Hello, calculus students. I hope things are going well. This is section 4.7. We are here. What do I mean by that? Well, we are finally here, almost at the end of section 7. Chapter 4. We have one more section after that, but section 7 is about optimization. So we are going to be finding maximum and minimum and a few other things because we are in the multivariable calculus. And so this is how we apply what we have learned so far. So section 7 is actually a long section because we have local maximum and minima first, and then we have absolute maximum and minima. Now, before you watch this video, I want you to go to the module and then download those two worksheets. We will use one before the real lesson and one afterwards to review and to use as application problems, okay? So make sure you download those two worksheets and then you go on to watch the rest of this video, okay? So let's get started. Okay, so what I'm trying to show you here, what you are seeing here as I share my screen is it's a worksheet entitled Math 213 Extrema of Single Variable Functions. Wait, it's single variable? Yeah, I wanted to review, as I almost always do, before I go on to a new section in Calculus 3, I wanted to review the key elements or the key ideas from Calculus 1. So we go back to Calculus 1 just for a while, right? And then I need to review some of the most important facts about optimization, okay? All right, so here are the facts. I think I have 7 facts or something like that on this. All right, and we'll go through this fairly quickly because this is not the main point of our multivariable calculus optimization. But let's first assume that we have a regular function, a function from the real, the set of real values to the set of real numbers. Okay, so this is a real valued function defined on the reals, and it's continuous. Okay, we say x is a critical point. So you're thinking of a function like this, all right, and maybe just make it up and down like this. Let's try to make it smooth, and maybe we'll have a little interesting point like this. Okay, how about that? How about this? All right. And so let's say this is 0, this is A, and this is B, and this goes on, okay? And continuous means, there's no hole or gap or whatever. X is a critical point, okay? I can see here's a critical point, right? If what? The derivative at X is equal to 0 or undefined, all right? So that's the definition you learned for critical points. I can see another critical point here, because the derivative seems to be 0, and I can see another critical point, right? So at this point, looks like the derivative is 0, the derivative is 0. Here, the derivative is undefined. All of these are critical points, all right? A relative, or every relative extrema. Now, by the way, we have what we call maximum. We also have what is called a minimum, all right? And both of these are called extremum and extremum. These are all like Latin endings, um ending. And then if you make them into plurals, these are become maxima, not like a Japanese made car, but it's the plural of maximum is a maxima. And then we have the plural form for minimum, which is minima, and both are called in the plural extrema. Okay, so when you talk about one point of this, we say an extremum. If you have more than one, those are called extrema. All right, so much for a lesson in Latin and grammar. So every relative, or relative means local, okay? Relative and local are exactly the same. Think of these as interchangeable, synonymous in this context. Because relative is the opposite of absolute, and local is the opposite of global, and they basically mean the same thing. All right, so every local extremum, meaning maximum and minimum, okay? And you can see one here and one here, okay? They occur at a critical point. Now, it's important for you to know that the converse does not happen. So in other words, not every critical point represents a point of maximum, or minimum. Right? And so here's a classic example. If you have x cubed, there is a point. This is a critical point because the derivative is 0 at this point, but it's not. It's a critical point, but it's not a relative or local maximum or minimum. So every local maximum or minimum occurs at a critical point, but not every critical point represents a local minimum or maximum. All right, and then we have this theorem, which is sometimes people don't know about this. EVT, this is an extremely important theorem, and it is called the extreme value theorem. And the word extreme has to do with maximum and minimum. All right, if f is continuous on a closed and bounded set, for example, on this interval, a closed interval, it's important for you to note, it has to be a closed interval and bounded interval, like the closed interval from A to B, then f has an absolute maximum and absolute minimum. Okay, I'm talking about a continuous function. Every continuous function defined on a closed interval, listen carefully, on a closed and bounded interval it's guaranteed to have an absolute maximum and a minimum. Now, this may sound silly. You may think, of course, it has a maximum and minimum. So at this point, for instance, here, let me just point out in my sort of a random picture, this y value at this point is the absolute maximum, right? And you can see this point is the absolute minimum because this is the lowest point and this is the highest point, and the y value is called the absolute maximum or absolute minimum. Okay, so what's a big deal? Of course, functions have absolute maximum and minimum. Well, not so if you think about this. All right, so for instance, if you have y is equal to x cubed on the entire real line, okay, on the entire arc, okay, you realize that this has no maximum or minimum, right? What do you mean? Well, because this continues to go on and this continues to go on down there. So if you don't have a boundedness, okay, you are not guaranteed to have a absolute maximum or minimum. Okay, I mean, same thing happens with y is equal to x or y is equal to x squared. X squared does have a minimum, but not the maximum. All right. Also, if you think about this, y is equal to x, that's clearly, just a straight line, right? But if you define this just on 0 to 1, so this is your picture, okay? Now, this is definitely bounded, because the entire domain is between 0 and 1, but it's not closed because it doesn't have the endpoint, okay? Now, do you realize, I hope you do, but do you realize that this function, a very simple function, y is equal to x, from 0 to 1, not including the endpoints, does not have an absolute maximum or minimum, right? Or did you know that? You would say, well, 0 is the absolute minimum. No, because there is no point where the y value is 0, right? Remember, this point 0 is excluded. And there is no maximum point because x or y never reaches 1, right? As x approaches 1, y also approaches 1, but it never gets to 1. So technically speaking, and again, mathematically or precisely speaking, there is no maximum or minimum. So the idea is that the extreme values, like the absolute maximum and minimum, is not guaranteed unless you have a continuous function and closed and bounded. Oh yeah, one more thing. What happens if it's not closed? Okay, and so here's an example. If it's closed and bounded, but not continuous. Okay, so here's an example. I can create a function like this, where this is open, and let's say we define it here. This is definitely continuous, but this function on the closed and the bounded interval 0 to 1, okay, this has no maximum or minimum, right? Because you would think that this is the maximum point here, but it's not because there's a hole here. There's also a hole here, so there is no minimum, right? So I can create a sort of a nasty function like this on the closed and bounded interval, but there is no absolute maximum or minimum if it's not continuous. All right, so the extreme value theorem is, again, extremely important theorem, which says continuity plus closed and bounded guarantees a maximum and minimum value. By the way, closed and bounded by another famous theorem by someone else is called a compact set. And so every compact set has, every continuous function, real value continuous function on a compact set has an absolute maximum and minimum. All right, so the method of finding absolute extrema. Okay, now this is another important point here. How do you find absolute maxima and minima? It's been a while since you took Calculus 1, probably a year, and you may remember this. You may remember this incorrectly, and that's the reason why I'm explaining this. Method of finding an absolute extrema or extremum on A to B. All right, so first, you find all critical points. On A and B. Right, because I mean, you may have a function like this, and let's say you have another function here. This time it's like this, okay? And so here's a critical point. Here's another critical point. Seems like, right? And so it could be that the absolute maximum and minimum could occur at these points. So find all the critical points. I call them usual suspects. You know, I mean, you round up the usual suspects because these are the points where if an internal maximum or minimum occurs, they have to occur, remember, relative ones, local ones, have to occur at critical points. But not every critical point is a maximum or minimum, not even locally. All right, and then you evaluate F at the endpoints. Now, why do I do that? Well, because the endpoint actually may be not a critical point, but it could be the highest or the greatest value of the function on that interval, right? So you don't actually have to use the first or second derivative test. If you don't remember what these are, you may want to look up in your calculus book, or you can just go look at right under this, right? Because the point here, the important point I'm trying to make is if you're looking for the absolute maximum or absolute minimum, okay, you don't need the first derivative test or the second derivative test. All you have to do is to find critical points and the endpoints and evaluate the function at the endpoints and at all critical points. All right, now you'll have this point and this point, the endpoints, and this point and this point. These are the critical points. All right, you have a finite number of points, in this case 4, and then if you just find f of x at these 4 points, the biggest number is the absolute maximum. The smallest number is the absolute minimum. Done. Okay, you don't have to worry about all the tests like the first and the second derivative test. Now, the first derivative test is the one that says if you have a critical point at this point C, okay, and watch, here's point C. If the derivative changes from negative to positive near C, then f has a relative minimum. It makes sense, right? And of course, if it goes from positive to negative, then you have a local maximum at that point. Right. So you have probably seen a sign chart that says, you know, like f of x, f prime goes from negative to positive, and therefore it must be, C must represent a point of a local minimum and so on. Okay. The second derivative test is not about the second, I mean, it's about the second derivative, but it's not about the concavity. Some people think the second derivative test is about concavity. No, it is not quite, right? It's still about finding a maximum, local maxima or minimum, right? If f is differentiable and if C is a critical point, same setting, right? And if the second derivative is positive at this point, what does it mean if the second derivative is positive at this point? That means the first derivative is 0 because it's a critical point, and the second derivative is positive. The second derivative positive means it's concave up like this. So this has to be a relative minimum, okay? If the second derivative is negative, likewise, then it'll be representing a local maximum. Right? That's called the second derivative test. And the point I'm trying to make is these are the things you do not use. Did you hear that? You don't use these if you're looking for absolute extrema. All you have to do is to find the usual suspects and the endpoints and evaluate the functions, okay, at each of these points. And the greatest value is the maximum and the least is the minimum. done, okay? Only when you look for relative or local maxima and minima do you use first and the second derivative test. This is not so important in calculus 3. We have a new version of the second derivative test in a moment. All right, number 7, if C is a critical point, F may have a relative maximum, but it doesn't have to. Okay, that's what I was saying at the beginning. All right, so with that, I hope you understand this. If there's any part of this you don't understand, make sure you review your calculus 1 and then get back to our lesson on 4.7. All right, I'll pause this for a moment right now, and then we'll go to the next segment of the video for 4.7.